Necessity of both conditions for similarity. Welcome, everyone. Before we dive into today's lesson, let's take a moment to recap. In our previous sessions, we established the formal definition of what it means for two polygons to be similar. Now, it is crucial to remember that for two polygons to be truly similar, we cannot just look at one feature. Two specific conditions must be satisfied simultaneously. First, their corresponding angles must be exactly equal. Second, their corresponding sides must be in the same ratio, which we also call being proportional. A very common misconception I see students making is assuming that satisfying just one of these conditions, either the angles or the sides, is enough to prove similarity. To clear this up, in this subsection, we are going to perform a step-by-step demonstration. We will examine specific cases where only one of these conditions is met, to show you exactly why both conditions are absolutely necessary to guarantee similarity. Case 1. Equal angles but non-proportional sides. Now, let's put that theory into practice. To understand why we can't just rely on one condition, let's look at our first case study on this slide. We are going to compare two very familiar quadrilaterals, a square and a rectangle. First, let's perform step 1, which is to analyze the angles. If we look at a square, we know that every single internal angle is 90 degrees. Now, if we look at a rectangle, we see the exact same thing. Every internal angle is also 90 degrees. So, if we compare them, we can see that the angle of the square equals the angle of the rectangle, which is 90 degrees. Based on angles alone, you might be tempted to say they are similar, right? But we aren't done yet. This brings us to step 2, where we analyze the side ratios. Let's assign some variables. Let's say the side of our square is represented by the letter S. Since it's a square, all 4 of its sides are equal to S now. Let's look at our rectangle. Let's call its length L and its width W, and we must remember that in a rectangle, the length is not equal to the width. Now, let's compare the ratios of their corresponding sides. If we take the first pair of sides, the ratio is S over L. If we take the second pair, the ratio is S over W. Because we already established that L and W are different values, it follows mathematically that S over L does not equal S over W. This means the sides are not proportional. So, what is our conclusion here? Even though the angles are identical, the sides are not in the same ratio. Because that second essential condition failed, we must conclude that a square and a rectangle are not similar. This sets the stage for our next slide, where we will look at the opposite problem. What happens when the sides match, but the angles do not? Case 2. Proportional sides but unequal angles. Now, we've just seen in the previous example how having equal angles isn't enough to guarantee similarity. But what happens if we look at the opposite scenario? Let's move on to case 2, where we examine what happens when the sides are proportional, but the angles are not. To illustrate this, let's consider two specific shapes, a square and a rhombus. First, let's perform step 1, analyzing the side ratios. By definition, we know that in a square, all 4 sides are equal in length. Similarly, in a rhombus, all 4 sides are also equal to each other. Now, let's say the side of our square is represented by the variable a, and the side of our rhombus is represented by the variable b. If we compare the corresponding sides, the ratio of the first pair is a over b, the second pair is a over b, the third is a over b, and the fourth is also a over b. As you can see, the ratio is identical for every single side. This means the corresponding sides are perfectly proportional. However, we cannot stop there. We must move to step 2, analyzing the angles. In a square, the internal angles are fixed. They are always 90 degrees. But in a rhombus, while the sides are equal, the angles can vary. As long as the opposite angles are equal, the shape remains a rhombus, and these angles are generally not 90 degrees. Therefore, the angle of the square does not equal the angle of the rhombus. So, what is our conclusion here? Even though we have achieved perfect proportionality in the sides, the corresponding angles are not equal. Because that second essential condition has failed, we must conclude that a square and a rhombus are not similar. This leads us to a very important realization, which we will summarize in the next slide. Similarity is a two-part requirement that must be met simultaneously. Summary of the requirement. Now, I want to step away from the abstract geometry for a moment and give you a way to visualize this concept in a real-world context. Think about when you are working with a digital photograph on your phone or computer. Imagine you are resizing a photo. If you click and drag only the corner of the image, you'll notice that the photo grows or shrinks, but the content stays perfectly natural. This is because you are maintaining what we call the aspect ratio, meaning the sides remain proportional, and the shapes within the photo remain the same because the angles are preserved. In mathematics, we call this a similar transformation. However, consider what happens if you grab just the top edge and stretch the photo only vertically, or grab the side edge and stretch it only horizontally. The corners might still be 90 degrees, but the proportions of the sides have changed. The people or objects in the photo will look unnaturally tall or unnaturally wide. The resulting image looks distorted because it is no longer similar to the original. This brings us to our main point. For two polygons to be mathematically similar, they must be identical in shape. This cannot happen by chance. It requires both the angular framework and the side proportions to be preserved simultaneously. As we will see in our summary and key takeaways, if even one of these elements is lost, similarity is lost. Key takeaways. Now that we have examined those two specific cases, the square and rectangle, and the square and rhombus, let's bring everything together for a final summary of the requirements. First, let's recap our two essential conditions. Condition 1 is the angular framework. The corresponding angles must be exactly equal. Second, we have the side proportions. The corresponding sides must be proportional, meaning they all share the same ratio. This leads us to the fundamental rule of similarity. You can think of this as a logical and statement. In mathematical terms, we say that similarity is equivalent to, or if and only if, both condition 1 and condition 2 are satisfied simultaneously. It is crucial to remember that this is a strict requirement. If even one of these conditions fails, if the angles don't match, or if the sides aren't proportional, then the figures are simply not similar. As we move to our final slide, we will look at some common pitfalls to avoid when applying these rules in your exams. Common mistakes. First, be careful not to assume that equal angles are enough to prove similarity. It is very easy to look at two shapes, like a square and a rectangle, and think they are similar because they both have 90-degree angles. However, as we saw in our first case study, if the side ratios don't match, the similarity fails. So, always remember to check those side ratios. Second, do not fall into the trap of assuming that proportional sides are sufficient on their own. You might see a square and a rhombus and notice that all their sides are scaled by the same factor. But as we explored in our second case, if the internal angles are different, the shapes are not similar. You must always verify that the angles are also equal. Finally, try not to confuse similarity with congruence. While these two concepts are related, they are not the same. Congruence requires the shapes to be identical in both size and shape, whereas similarity allows for different sizes, provided the fundamental shape, the angular framework and the side proportions, remains unchanged. Now, as we wrap up this lesson, I want to touch upon some common pitfalls that students often encounter when working with similarity. Being aware of these mistakes will help you avoid errors in your proofs and calculations. Keep these distinctions in mind, and you will have a much stronger grasp of geometric similarity.